Hi everyone, so this week we are reviewing force diagrams and connected particles, and I thought that the best way to do this probably was to go through a couple of big chunky questions, and hopefully lots of stuff will come up and it will be good revision for you and it will identify any areas that you might need to go back and do some work on. So the first question I've picked is the Edexcel June 2014 M1 paper, which is the old mechanics paper, and it's question 7. And we've got sort of a straight up and down connected particles problem, but we have this BC unit, which is 2 different particles. I would always recommend when you start a force diagrams question, drawing out the diagram again for yourself, making sure that you add in all of the different sort of forces and lines and things that you're going to need to have on your diagram. So I'm going to start this problem because I'm being asked to find eventually acceleration and tension in the string, with B and C being a combined unit. And we'll split that apart later when we need to think about it a little bit more. But because they're stuck together, it's basically like if you wrap that up, you wouldn't know they were 2 separate things. So that's what we're working on there. Don't forget weights act straight down, so we've got 3mg on our particle A and a combined 4mg for our BC block. Our tensions will be acting vertically upwards, and I always divide my string and also draw what's happening to the pulley as well. So the pulley is experiencing 2 tensions downwards on either side of it. And it's all the same tension, but I like to put that in there. I know it adds a little bit more complexity. If we release this system from rest, then the object will move so BC will slide down and A will slide up. So I want to put some accelerations on there. And of course, because we have a light and an extensible string, that acceleration is the same throughout the system. Right, that is no different whether you've got 1 particle, 2 particles, or anything like that. The thing that seems to freak people out with connected particles is they go, well, how do I unpick that? What the tension does in that string on that connected particle is allow you to essentially ignore anything else that's going on with the other particle. So your tension allows you to think about just A on its own, as long as you put tension in there, or the BC unit on its own as well. So we're going to take all of those ideas and start looking at question or part A. So here I am going to draw 2 separate diagrams because this is the beautiful thing about this tension. So here I've got a diagram for A. Now, the tension allows me to completely ignore B and C for a second and just think about what's happening on A, which is this. Now that's just a single force diagram. It should be possible for us to create an equation for this. We are moving, and we're moving upwards, so we've got Newton's second law applying here. F equals ma. Now F, don't forget, is the net force. So tension is trying to drag this thing up, so we'll put that in as positive. Notice my arrow helps me figure that one out. The weight is trying to slow it down, it's trying to drag it down. So we want to put that in the kind of opposing direction, or as negative. Our mass is 3m, and we don't know our acceleration. Right, m is a unit, so we're not worrying about that bit, it's just like a constant. G is 9.8, so my 2 unknowns are tension and acceleration. If I have 2 unknowns, I'm going to need a second equation in order to be able to find them out. That is fine. I can just go looking at this BC unit thing that I've got going on over the other side, which has a combined weight of 4mg. Still tension going up, but this one's trying to move down. So if I apply the same equation, but this time with a F equals ma with my sort of positive direction, or my direction of motion being down, the thing that's trying to encourage it down is the weight. That's working in the direction we're moving, so that's good. The thing that's trying to slow it down then is the tension. So that will go in as an opposing force, or negative. My mass this time is 4m, and I don't know my acceleration. Well, now I have 2 equations, 2 unknowns, and I can solve simultaneous equations. I'm going to rearrange equation 1 to say tension equals 3ma plus 3mg, and then substitute that in where I see tension in the other equation. So 4mg minus tension, which is actually 3ma plus 3mg equals 4ma. Sorting that equation out then, we end up with 4mg minus 3ma minus 3mg, notice both of them are inside the brackets, so they're both negative, equals 4ma. If I just rearrange all of that, I'm going to get that mg equals 7ma. Now, there's an m on both sides of the equation, so that can cancel, and we want to know what our acceleration is, so a is g over 7, which is exactly what we wanted to show, that, so do make sure you pop a little conclusion in, whether that's a tick, smiley face, a QED, as required, or Halmos's tombstone, doesn't matter what you put there. Good, so that's our part 1. Part 2 says find the tension in the string as A ascends. So we just need to take our value of acceleration and plug that into the either equation. Actually, for tension would be fine, but my equation 1 is rearranged to say T equals, so that's quite nice. So T will equal 3m g over 7, which is our A, plus 3mg, which works out to be 24 over 7 mg. Notice that these two parts of the question occur and then the marks come in afters. What that should say to you is that you can do those two parts, part 1 or part 2, in either order. Your examiner is going to mark that whole response altogether. They're going to look for a value of T, look for a value of A, and not necessarily have seen part 1 and part 2 attached to it. So if you see two parts and the marks come after both parts, you can do either part in either order. Okay, and then the rest of the question, we're going to take some of these ideas and we're obviously going to move it on forward. Don't forget, with connected particles and force diagrams, Suvat will nearly always appear in a big question because you're talking about motion in a straight line. Suvat's that exactly. Okay, so in part B, we've been given some information before. There's always a temptation to skip over that. Please do read it. At the instant when A is 0.7 metres above its original position, C separates from B and falls away. Fine. Okay, so we're now going to have to change our diagram. We're told that A doesn't reach the pulley, so that means it doesn't go slamming into the pulley at any point. We need to find the speed of A at the instant when it's 0.7 metres above its original position. That instant word there, that's really key. What that means is it's on the split second before B and C separate. So we're actually using all of our information from before. We're asked for a speed and we've been given a distance. We have acceleration from previously. That's definitely Suvat. So we'll set up our Suvat diagram or Suvat table. And we have travelled 0.7 metres. We started from rest, we're trying to find this speed v, and our acceleration from before is, well, we need to think about which way this thing is moving. A is moving up, and our acceleration was also up. So acceleration here is positive g over 7. Okay, Suvat equation containing v, u, s and a is v squared equaling u squared plus 2as, and we just plug in what we know. So v squared equals 0 squared plus 2, g over 7, which is 9.8 over 7, s is 0.7. All of that can go in my calculator. V squared comes out as 1.96, and so v is 1.4, and don't forget your units. So there's part B. Okay, part C, find the acceleration of A at the instant after C separates from B. Well, it's not going to be g over 7 anymore because g over 7 was calculated on the fact that B and C were sort of stuck together in a weight of 4m respectively. Now we don't have that. So we should redraw our diagram and have a look at what we do have. A hasn't changed. A is still 3mg as a weight. It's still got tension going upwards. It's still attached to a pulley. But now I only have 2 mg because C has fallen away, so I'm just left with B. Stopping for a second and just thinking about what would happen, that structure now is going to want to move so that A falls down because A is the heavier one. So actually we're going to have a change in direction of our acceleration. The overriding force is going to be that A is going to want to pull the thing down, where before, because B and C was a combined heavier object, it was moving in the opposite direction. So our acceleration has now changed direction, which means when we set up our equations, if we look at A again, we've still got F equals ma, we're still in motion, but this time we're interested in A as it's going down. That's going to switch everything around for us. So the weight is encouraging it down, 3ma. The tension is trying to slow it, so that will go in as a tension, as a minus, sorry. And then mass is 3m, and our new acceleration we don't know. For B, we're going to be going, still F equals ma, we're moving, but this time we're moving up. So for this one, tension's encouraging it upwards, it's trying to drag it up. Its weight is trying to slow it down, so that's 2mg. Mass is 2m. And acceleration is A. We've got a similar sort of problem as we had before, 2 equations, 2 unknowns. So we're going to do exactly the same thing, rearrange the B equation for T, substitute it in, resolve, it's exactly the same maths as you did in part A, and you're going to end up with acceleration equaling G over 5. Our last part then is part D, find the greatest height reached by A above its original position. Okay, so even though we have said that our sort of motion will eventually be down, we're in a kind of upward inertia, if you like, in the sense that A is on a trajectory up and its acceleration is now starting to try and pull it down, but it's not going to instantly switch direction. That acceleration trying to pull it down will slow it first. So A has become sort of, it's at a point when it gets acceleration changed. It's at a point where it's 0.7 meters above the ground, moving at a speed of 1.4 meters per second. And then from this instant onwards, the acceleration is trying to slow it down by accelerating at g over 5 downwards. So it's going to travel up for a bit, and then it will get to a point where it's gone slower and slower and slower and slower. It will reach 0 velocity, and then it will start to come back down again. Think about throwing any object into the air. If it didn't do that, it would never return to you. So we can set up a final Suvat here. We're interested in the height, so I don't know what it displaces to. At the instant when this whole little bit of our problem starts, it is moving at 1.4 meters per second, because that was its speed the instant B and C separated. We know that at the highest point, its velocity is 0. And we're going up at the moment, so up is positive, but we know that its acceleration is trying to slow it down, so our acceleration is going to be negative. And we're trying to find S, our displacement. Okay, same equation because I've got the same things. So v squared equals u squared plus 2as. And we're going to plug in everything we know. 0 equals 1.4 squared plus 2 times minus 9.8 over 5 times by our distance. Rearrange that, we get our distance equals 0.5 meters. So our total distance then is the 0.7 it travelled before this little part of our problem started, and now it's travelled 0.5 meters additionally, and so we end up with 1.2 meters as our total travel